welcome again. Good morning, good afternoon, good evening to everyone to our first webinar on what's new in MPEG. My name is Christian Timmerer and I'm the moderator of today's webinar. We have a couple of topics and speakers prepared that will give you an overview about what happened at the last MPEG meeting, the 131st MPEG meeting. And we will start with a short intro by Jörn Ostermann, and then we will follow the schedule as proposed and as prepared. For the discussion, please go to Slido. I have posted the link in the chat, and it's also available on the website that have been communicated before. Please also, you can feel free to upvote the questions there, and then we will take it from there to have some Q&A at the end. The entire program is scheduled for 1 hour for the presentations and then also the questions, but we have reserved for 1 hour and a half in case we have more questions and we need more time to answer. Also, the video or the webinar is being recorded, and we will try to make at least the presentation available for on demand at a later stage. And I'd like to give now the floor to Jörn for his welcome.
Okay, good morning, good afternoon, ladies and gentlemen. Welcome to our webinar on MPEG. MPEG is in a phase of change. We had 130 meetings with our founder, Dr. Leonardo Schierraglione. He retired, and this month, at the beginning of this month, we had the first meeting without him. So I guess there's some sort of change. We would like to report what happened at the last meeting, and we would also like to show you what is a significant work that is ahead of us. And therefore, we have all the chairs of the MPEG subgroups here, and they will report to us what happened at the last meeting, what standards are ongoing, what standards were finished. At the end, we will also look at the roadmap to show you what is ahead of us. And all of this will continue, although some of you might have heard there's some restructuring going on that happens to MPEG, but in the end, MPEG will continue as it is, just with a different internal ISO structure. So without further ado, let's start with Young-Kwon on MPEG systems.
Hello, everyone. So it's my turn. Give me 1 second. Okay, let me turn on my video as well. I will have a short presentation of what happened in MPEG systems, what's been kind of interesting new items, new topics from systems. Okay, I'm sharing my screen now. Good. So I will explain a little more about what has been done in terms of Carriage of VBC and EBC, both are new codecs coming into the market in terms of MPEG systems. Okay, so this is a kind of overview general diagram of how kind of Carriage is supported by MPEG system standard. When you say Carriage, it normally means for the first time people are hearing about Carriage in MPEG terms. It means both the storage and delivery of data. Okay, so whenever kind of new video coding standard appears and there's need to be supported by multiple system standards, starting from MPEG-2 systems, which is kind of one of the oldest but most widely used, standard. So we need to define how that codec can be carried over MPEG to TS. And there's a lot of other standard based on the ISO basic media file format. So we don't normally touch the part 12 of MPEG-4, which defines a base kind of mechanism based technology for ISO basic media file format. In the case of the codec is using null unit as a kind of syntax element, syntax structure, and we start from adding that codec support to kind of MPEG-4 part 15, which is called null unit based file format. And recently we've been working on we've been working on the image file format, how to store the kind of video codec data as an image or image sequence in ISO basic media file format. So we also need to extend that. Some of them will be, some of things will be kind of, referencing, now file format specification as well. And then there are two other kind of, the application format, which defines more, precise definition of interoperability points, other words, brands. Defining one for CMF segment and another one for image file format. And at the same time, we also need to work on extension of Dash, since Dash manifest has some extension for specific codec related aspect. And also we need to work on the carriage of video data over MMT as well. So I will explain more about, what has been done recently in MPEG in this, context. The first thing, as I mentioned, is the extension of the carriage of VVC data in MPEG to TS and EVC data in MPEG to TS. Here I'm kind of explaining, I'm providing the full name of the project if you're interested in looking at the more detail in terms of technology. Currently, it's the second stage called the DAM, draft amendment, and then it'll be a kind of, it'll reach the final stage in April 2021. So major features included in that, spec is the essential part of, carrying the video codec onto the MPEG to TS, including, how to align VVC data with, pass packet, packetized elementary stream packet. And there are several descriptors, needed to carry the video data over MPEG to TS. So we are also kind of, extending that. And also one of the important thing is to aligning VVC HRD descriptor with the TSTD extension using HRD descriptor. That's also kind of, added. And there should be some constraint how to kind of, carry, transport VVC bitstream over the MPEG to TS. That is also being specified. And TSTD extension, the model needs to be, TSTD extension is also kind of being prepared for both single layer VVC case and also temporal layered video subset case as well. Same happens for the carriage of the EVC as well. So it has been started one meeting cycle behind. So it's currently in CDM stage, the first stage, and it'll reach kind of, July 2020 first as a final, standard, draft standard. Same things goes here that, the EVC data alignment and the descriptors and constraints will be defined, and also TSTD buffer model extension will be specified for that standard. Okay. Moving on to next topic, which is carriage in ISO based media file format. As I mentioned, that main things happening here in MPEG-4 part 15 are unit based file format. The there is an amendment including both VVC and EVC carriage in a single part, single amendment. Currently, it has reached the second stage, DEM, and it will reach the final stage in April 2021. So there are two sections, one including VVC support and another one including EVC support there. So it's saying here that, basic, definitions kind of work on here. So since, the file format used kind of, sample definition, and then that, becomes a core of, synchronization and order delivery, processing. So mapping what is the kind of, sample of the video data to file format is important. And also there's a need to define the subsamples, which is a kind of smaller than samples, and sync samples, where do you start decoding, and decoder configuration record and so on needs to be defined as well to configure the decoders correctly. And in terms of layering, currently single layer is being defined. Also, there is a kind of multiple layers also defined. So, so when you have multiple layers, then it could be stored in a single track, or it could be stored in a multiple track based on your kind of preference. Both are supported in this specification. And when there is a kind of more than one layer, then there's a kind of also need to be supported in this case as well. So the same goes in EVC, but a lot simpler. Currently EVC, storage only, single layer case is being defined here. So there's a little bit difference between the EVC carriage and VVC carriage. Next one is about image file format extension. So there's also one single amendment containing both VVC carriage and EVC carriage, which is currently CDM stage, first stage, and then it will reach the final stage in July 2021. Same as before, there's a section about VVC related features and another section about EVC related features. The same goes here, that a lot of definitions about, mapping EVC and VVC into the kind of file format structure is happening here. And for VVC case, there's two brands has been defined, one for image and image collections, and another one for, the image sequences. They don't define specific codec profiles yet related to this, image profile. EVC case, there has been, 4 different brands defined in this spec to support baseline profile and main profile separately. So EVB, I, and BS used for baseline profile, and MI and MS used for main profile as well. So both main profile and baseline profile are separately specified and supported for this case. And the MMT carriage has been defined only for EVC at this stage, and it has reached the first milestone, and it will reach the final stage in July 2021. There's nothing kind of big specified here, because the MMT carriage means simply defining what's the MPU for EVC, and there is a constraint to use a CMAP track constraint format for MPU definition for EVC. Then that will be the kind of most of the thing. So I think this will bring my the last slide. So maybe next one.
Thank you, Young-Kwon. And it seems like we go in the order as we usually do the presentations of the MPEG plenary, and the next one then, according also to the poster, would be Bart, providing us some overview about what's going on in MPEG video, and specifically related to MPEG immersive video.
Okay, 1 second. Okay, so I will explain something about MPEG Immersive Video. MPEG Immersive Video is in MPEG based on the video-based visual photometric coding standard, which is the base text of the standard that includes video-based point cloud coding. More on this later by Marius. And MPEG Immersive Video is basically a combination of using a V-PCC bitstream with MIV extensions. And I listed the schedule here for both standards. So for MIV, and the MIV will be aligned to the second edition of V-PCC and V-PCC. So MIV is part 12 of MPEG-I, and V-PCC is part 5. And the committee draft that we are working on now to release this Friday is will be based on the FDIS of part 5. And the schedules have been aligned, so that's why the DIS of MIV will be 1 cycle later than you would typically expect. So this is an example of a test material that we work with. You can see on the right a diagram showing the camera layout. So there are 15 views. In this case, they are photorealistically rendered. Each view is 4K by 2K. Omnidirectional projection, and then each view there is geometry, which is like the depth range per pixel, and the texture attribute color. And on the left you see a rendering where you go through all those views, and then you see a synthetic view basically. So that's what you can do with this content. So that's the input of the encoder. Just to provide another example, here you can see, if it works, yes. Here you can see an example of a 4x4 camera array, which is having physical cameras with estimated depth, with perspective projection. And this is also something that the standard can handle. So the model of the codec is that you have such input, then this is encoded into a V-PCC bitstream. Then this V-PCC bitstream is decoded and rendered, and then the reconstruction is not one of these source views, which would be the typical thing to do for a video codec, but instead the reconstruction is for any position within the viewing space. So this is where that's why we call it a MIF decoder / renderer, because it's basically doing both. And then the renderer is informative, and the decoder is specified in the standard. The data, the way that the bitstream is represented is from all the source views, only a couple or maybe only one is fully represented, and from the others, patches are taken. And this is similar to point cloud coding, you will realize soon. So this is an example of an atlas where you can see there's one full view, and then there are some small patches. In this case, the geometry and the texture are drawn in the same plane for compactness. And then the viewport video, you have just seen an example of a viewport. That's the output. So it could be the same format, the same projection as the input, but in this case, the output is perspective and the input is ERP. And the bitstream structure is, so the full syntax is basically coming from V-PCC. So where you have a stream with a parameter set in the beginning, and then multiple V-PCC units. And then V-PCC units of the same type are concatenated to form a subbit stream. And each subbit stream is composed of access units, which are basically the frames. And then there are multiple subbit streams. So you have subbit streams for the attributes. So MFV only has a texture attribute, but V-PCC also has other kinds of attributes, just as reflectance or transparency. And then also the geometry. So those are the video subbit streams. And then you also have something called a common atlas data, which has the view parameters, which might also be updated frame by frame. And then you have the atlas data, which is the relation between the patches and the projection planes. These can also be updated, maybe not at every frame, but sometimes every second, for instance. So the encoder, according to the test model, which is just an example of an encoder, first perform some automatic parameter selection. For instance, checking the geometry quality, choosing which views to represent fully and which ones are as additional views to take patches from, and then also to choose the frame sizes for the atlases. Then the first step is to prune the views. So for every view, the pixels are relevant are marked and other pixels are removed. And then based on the pruned views, patches are taken and atlases are formed. So then the output of this first preprocessor part of the encoder is you have the parameter set, the view parameters, atlas data, and then the raw video data. And then a regular video codec is used. We typically use AGVC. Sometimes we also use V-PCC for experiments. And then all these sub-bit streams are multiplexed into a single bit stream, and maybe also with side messages. And then the decoder renderer, everything is decoded. Then the geometry is upscaled. Some patches may not be visible in the viewport, so they can be called to save on rendering time. Then the pruned views are reconstructed. So you go back to the source representation, except that not all pixels are available. And then the view is synthesized, interpolated is another word for that. And then there might be that there's some pixels are missing, they are in-painted. And then it could be that, as shown before, there's a viewing space. If the viewer or the viewport might be outside of the viewing space, you probably want to show something different. And what is implemented in the test model is to fade. So when you go outside of the viewing zone, then the viewport just fades to gray. So in discussion, it's MRV is a flexible standard for multi-view video with depth. It's agnostic to the video codec. As mentioned, we tested by JVC and VVC, but more could be added. And the MIF main profile is basically a subset of V3C with some MIV extensions. And it is easy for MRV to use more of the features available in V3C, such as occlusion video data or multiple attributes. I didn't want to go into too much details because I didn't know the audience specifically. And then there are also MIF-specific extensions, such as using coding per groups of views or auxiliary atlases and even object-based coding. So the test model is available publicly, so everyone can try. And I guess that if you want to use test material, then it's always available on request. So please participate in this activity. Thank you.
Thank you, Bart, for the update on MPEG immersive video. And we move now to the next part, which is on versatile video coding. And in this session, it will be presented by Jens Rainer Ohm.
Okay, hello everybody. So this is a report from the Joint Video Experts team, which is a joint team of ITOT and ISO-ISC, so VCAC and ITOT and MPEG and ISO-ISC. And I think the biggest news that we have to report here is that we are finally at the point where we have approved the first version of versatile video coding, an activity which started in April 2 years ago from the call for proposals, which was already joined with the two organizations. So this is twin text as previous joint standards. In ITOT will be called H.266, or it is called already, and in ISO-ISC it's called 23090-3. So it's part of the IMPEG-I standard. And there's a second specification which is called versatile SEI messages. This time we have really decided to put the SEI messages into a separate spec. Versatile here means not just, it's so universal that you could combine that with any other coding standards, and we will probably go that way, that in the future metadata such as SEI messages will be more formulated codec agnostic. And accompanying to that, we have the usual test model, which also has the corresponding software implementation. Very soon we will start also the standardization of a reference software, as well as conformance testing is already at a preparation to be started soon as a standard, and we are working on verification testing. I will show some initial results on some of the next slides. Subjective quality testing of the new codec. So what you can see here is some results in terms of objective metrics, measuring the peak signal to noise ratio as usual. This is for the random access configuration, which is the most important one for storage, streaming, and broadcast, where you have every second somehow an insert point where you can access the stream. And what is most remarkable that for the really high resolutions for Ultra HD video, in that case, the Ultra HD is only 4K, but similar is true for 8K video. We have a UHD, we have an average of 40% PSNR average gain over the corresponding reference implementation of HEVC. And so we are currently in the on the way to prepare visual subjective performance, and we already have some initial data on that, and more testing will be done up to the October meeting. And an interesting aspect that you can see here, we have designed this test in order to have points of the two codecs. So the blue one is HEVC, the orange one is VVC. We have designed test points that we thought we would have approximately same quality visually. And it turned out that the PSNR, so the objective metric that I reported on the last slide, was even slightly worse for VVC, but an interesting aspect is here that it almost over at least the lowest rate points, we observe that the visual quality is actually better, slightly better for VVC. So we have some good hope that we can really reach the proof that we see something like 50% data rate as compared to HEVC. So what does versatility means? Versatility means it's designed for a wide variety of types of video. We have already good support for camera capture, computer generated, and also mixed content. VVC already in its first version has built in some tools for specifically good for screen content, so for computer generated content such as computer graphics. And we already have support for standard and high dynamic range. Currently, with the given profiles with emphasis on 10-bit video, we're supporting various color formats, including already 444 RGB, also wide gamut. And we have good support without being too specific in designing specific tools for that, but we have built in good support for 360-degree video with various projection map types. Multi-view video is basically possible, including depth maps. And we already have some initial proof that also MPEG's video-based point cloud compression is much better compressed by VVC rather than HEVC. And maybe that we will later hear from the 3D graphics group on that. And we already have built in lossless coding support. More than that, there are some special features with a high-level syntax which are giving us more flexibility than HEVC was able to give. Particular, very flexible access mechanisms, and what's really notable is the new definition of what we call subpictures, which is a much cleaner concept than the tiles of HEVC were. Subpictures are, for example, good for accessing locally a 360-degree video, but subpicture could also be used, for example, to have a video conferencing system such as ours here, and just have use subpictures in order to show the videos of different persons and merge them together in one single stream. So the corresponding extraction merging mechanism at bitstream level, some special boundary handling, particularly for 360-degree video, or also refreshed after some broken communication. And we have already built in layered coding, including basically support for scalability operation, including spatial scalability. And this is done by a new mechanism which can also be used for better compression performance, which is reference picture resampling, but which can also be used at the same time for scalability. And we have the usual wavefront parallel processing, so good support for parallel encoding and decoding. And something which is new, general constraints information, which could identify tool usage at a very high level to identify whether certain tools are used in the bitstream or not. I don't want to go into details. This is just a rough overview of the coding tools that make this happen, in particular in terms of the compression performance. Again, quite something on improving the intra-prediction. By the way, for intra-only coding, it's not something like 40% measured in PSNR, it's something like 30%, but also that is noticeable because separate coding of pictures is typically more difficult than video coding. And the bulk of compression gain comes really from better interprediction again, also combined interprediction. We have some additional transforms built in, new loop filters, and some improvements of quantization and entropy coding. And all in all, this sums up in the good compression gain that I already reported. And just for more information, all the JVET documents are publicly accessible. We will probably make the slides available, so the numbers were on the very first slide, and here's where you can get them. And also the software is publicly accessible if you would like to play around with the software of VBC, or even do the comparison against HEVC. You can do that. So that's it from my side. Thanks for listening.
Thank you, Jens. And we move on to audio, which will be presented by Schuyler. Schuyler, please unmute yourself.
Okay, I guess should be working now.
Yes, thank you.
Very good, thank you. Okay, so the news from audio is in MPEG 3D audio, which is a standard of some time ago, we have a new audio baseline profile. And I want to talk about what that profile consists of, and also talk about the performance of that profile, and lastly, touch on the market uptake of that profile. So 3D audio, it was a standard from 2015, and it had a profile in it, the low complexity profile. And it enables or supports in the world of audio channels and objects, and also higher order ambisonics. So it was the first audio codec that was very flexible in terms of audio content and supported HOA. However, audio objects are a key component in enabling advanced personalization options in broadcast applications. So for example, when dialogue is an object, its level relative to the background music can be adjusted to obtain what's called dialogue enhancement. And of course, if dialogue is an object, then we can have multiple languages in a movie in a very simple way and in a very efficient way. What I want to report today is that there's a new profile. In about a year ago, industry requested a new profile dedicated to broadcast streaming, and particularly streaming of immersive music applications. Just this last meeting, this month, we completed the specification of that new profile in an amendment 2 to 3D audio, and this specifies what we call the baseline profile, which addresses this industry request. So details about the baseline profile: it's tailored for broadcast, streaming, and high quality immersive music delivery. It supports channels and objects. It's a subset of the first profile, the low complexity profile, and supports all advanced broadcast and streaming features. So for example, as I said, channels and objects, it additionally has loudness control and dynamic range control, which is needed for modern rollout of streaming media, audio broadcasts. It has a rich metadata set. It provides personalization and interactivity, for example, with object-based dialogue enhancement. It provides sample accurate splicing. So this is a new feature, and it permits you to do over-the-top ad insertion, which is really permits a stream broadcast to even put in personalized ads using over-the-top delivery. Details on the baseline profile. It enables up to 24 audio objects in what we call level 3 of the profile for high quality immersive music delivery, and we'll see high quality in a moment in another slide. Interestingly, it can be signaled in a backwards compatible fashion, such that baseline profile bit streams will be decoded by all MPEG-H enabled devices that support either of the two profiles. So a new LC profile decoder that's aware of the baseline profile can decode it because in fact, it is a subset of the LC profile. So how does that baseline profile perform? That's measured in a verification test report, which is available also from the most recent MPEG meeting. This is a public document and is available at the URL where public documents are posted. It reports the results of 5 subjective tests, which assess the performance of the baseline profile at different operating points. And bit rate, and that essentially means different bit rates and immersive audio use cases. The tests were conducted at 9 test sites. We see them listed there. They span the globe. There was a total of 341 listeners and more than 1 million subjective scores. So it's really a comprehensive test report that is an excellent portrayal of the performance of this new profile. There are 5 tests. They fall into 2 categories. So 3 of the tests use what's called the Mushra subjective quality scale. So this is all people listening to the coded audio. In one of the tests, it's highly immersive, 11.1 or 7.1 channel or loudspeaker presentation at a range of bit rates, depending on whether it's more or less channels, from 512 kilobits to 256 kilobits per second. Test 3 is slightly less immersive, 7.1 down to merely stereo, and the bit rates are lower. And for each of these tests, the score was excellent. So we are really into the high quality range at these rates. Test 4 is about headphones. It's the same content as test 2, but the MPEG-H profile renders for headphones, and the bit rate for all was something in between the 2 previous rates. Again, it scores excellent on the Mushra scale. 2 remaining tests are a little different. They use a different subjective test methodology. And in these 2, they achieve what is called the ITUR high quality emission benchmark of quality. And this is essentially the highest grade of quality for broadcast. And it's essentially what we call perceptually transparent. You can't tell the difference between coded and original at all. The first was very high quality, very high bit rate, very high number of channels, 22 channels at 760, excuse me, at 768. And the other test, which is labeled test 5, is 24 objects. Remember, that was the innovation or the new feature supported in baseline profile, coded at 1.5 megabits per second, presented as a highly immersive presentation over loudspeakers, again, achieving this broadcast, this high quality emission, or essentially subjectively transparent presentation. To conclude, I want to point out that this profile, which was requested by industry a year ago, which was finalized by MPEG just this month, is already rolled out as a service. So the 360 Reality Audio is a service that was announced recently, and it can now be enjoyed by consumers using these content providers. So quite a number of providers. And in this slide, I give some URLs for more information. And that concludes my presentation. Thank you.
Thank you, Schuyler. And we switch over to Marius and on point cloud compression.
Yeah. Hello, everybody. Let me share my screen first. Okay, I hope you all see my screen. Good. So this is the presentation for one of the items in the press release that is called point cloud compression. Actually, the name of the spec is even longer, and I hope you will understand at the end why it's so long. There are several activities in the 3D graphics group, but of course I will only focus on one flavor of point cloud compression. Okay, but first let's see what is a point cloud. Point clouds are like pixels, but not the same, in the sense that point cloud consists of a set of 3D points, but they are not ordered, and there is no relationship between them. Of course, we can still compute a 3D distance between points, but it's not the same relation as we may have in a picture between the neighbors. And in a point cloud, every point is defined as a set of 3D coordinates, x, y, z. And attached to that coordinates, we may have different attributes like colors, reflectance, and so on, depending on the application where the point clouds are used. Few examples here. So what you see is a video because we cannot stream point cloud directly currently. So I have to include it as a video in the PowerPoint, but actually what it is a point cloud. You may see some artifacts at the shoes or at the hair. This is a 3D representation that can be then rendered and viewed from any angle. But also there are more integrated applications, like we have here the example of the basketball sequence. You probably already saw it, where we have 3D representation of the player and a 3D60 video for the background. Or some other examples, like the one showed by Microsoft HoloLens, where the football players are represented as 3D objects in a volumetric space. One of the problems of this representation is that it requires a lot of points to be realistically rendered. So in the example here, for 800,000 points, we are talking about 1 gigabit per second in uncompressed domain. So there is no doubt that to be useful, that representation requires to be compressed. And this is what MPEG did in the last few years. There are some basic principles to follow concerning the compression of this representation. In general, we are talking about a very sparse occupancy of the 3D space. So, and this is because the objects are not represented by volumes, but by surface. In general, currently today, we are capturing the surface of objects. So into the pixel, into the domain, the pixel has 8 neighbors, but in 3D domain, point has 26, but many of them are not occupied, so are transparent, therefore cannot be used for doing prediction, for having good compression. As I mentioned previously, MPEG started in 2014. I will not go into the details of the timeline. There was a call for proposal like any other project. There were answers. Many of them focused on what we called dynamic dense point cloud. And we end up with having 2 solutions for compressing point clouds. One is the V-PCC. It's called V-PCC and is the subject of this press release and the subject of my presentation today. And the other one is GPCC, and I will have another opportunity in the future to present also GPCC. So we had the first committee draft in October 2018, but what is most important is that last 2 weeks, when we had our MPEG meeting, we published the FDIS of V-PCC. So the journey is ended for V-PCC, at least in the version 1, and activities continuing on GPCC. Okay, so coming back on the main principle that were used in V-PCC, the inspiration came from computer graphics. There are things that are quite well known, like displacement mapping, where the idea is to represent geometry as a modulation of colors or gray level in an image. And the other important idea is called in computer graphics texture mapping. So the color of an object in 3D space is represented in a 2D texture, and the correspondence between the vertex in the 3D space and the pixel in the 2D domain has to be stored. So these concepts are known from computer graphics, and they were applied to create a codec for point cloud. So the main idea is to project the 3D representation, here the point cloud, in 2D planes, and then to keep for each point that is projected the distance with respect to the plane and the color. Okay? But if we do so by using one single plane, we may have many points from the object that will project exactly in the same 2D plane. So therefore, the idea was to create several planes and project on several planes in the cube. Additionally, instead of projecting the entire object on the same plane, we patch the object, we segment the objects in a subset of point clouds, and each patch is projected on a particular plane. So they are the 6 faces of the unitary cube that are used for projection, plus 4 additional diagonal planes. And this careful selection was done to make sure that all the operations that are in the decoder and similarly in the encoder can be implemented in integer domain. So by doing so, we end up creating the patches, then projecting the patches at the end, and obtaining 2 images, one corresponding to the distance from the point, the pixel, to the projection plane, encoded here as a gray level intensity, and the other one copying the attributes, which are the colors in this illustration, of that pixel. So therefore, instead of compressing a 3D representation, we end up with compressing the equivalent 2D maps. It's not so easy in practice, because it may happen that still some points are projected in the same planes. So therefore, several layers of depth maps can be used. And also, even doing so, it may happen that still some points are missed. And in that particular case, there is a particular patch that is created called row patch, illustrated here below, where all these points are just put one after the other. And on the decoder side, to know which pixel from the 2D domain is used to reconstruct a 3D point cloud, there is an additional occupancy map that is encoded, indicating which pixel should be used. you may imagine not all the pixels from the 2D domain should be used to create a 3D point cloud. Okay, so this is the main idea of V-PCC, to project the 3D object into 2D planes. And guess what? These 2D planes are encoded by traditional video coding, and therefore the codec itself is a problem solved. There are a lot of work on trying to make these images more close to what a video codec is usually doing. One may observe that this is not what we are used to see when we are talking about video coding, but still the idea is here. So if we put that at work, we may resume it, we may summarize it in these numbers. We are talking about, for 100,000 points, at about 1 megabit per second. So objects like you saw previously with quite good definition, high quality, high visual quality. We are here talking about objects at between 4 and 7 megabits per second. More information is available. There are a lot of publications. Software is also available on this page, mpeg-pcc.org. And as a starting point, best would be to download the decoder and the encoder, and then start creating prototypes and even products from there. As I mentioned at the beginning, the title of the spec is longer, and that was also mentioned by Bart previously. So in the development of V-PCC, we realized that the idea of projecting a 3D space into 2D maps and then use video codecs to encode that 2D maps can be also reused by some other technologies. MIV is one of the case. V-PCC, of course, is the second one. And we are also planning that some other future objects like dynamic mesh coding to reuse this common framework. So therefore, the part 5 of MPEG-I, initially called V-PCC, was split in two. One is called visual volumetric video-based coding that provides the common framework. And the second part is V-PCC. So we are planning to use this V3C common part as a base for future technologies. And one, as mentioned before by Bart, is MIV, and the other one will be dynamic mesh coding. But that is the subject of a future communication. Thank you.
Thank you, Marius. And I think we will round up this presentation with a roadmap presented by Jörn.
Yes, thank you very much. So here we have our roadmap from January 2019 to sometime January 2025. As you see in the past, there are lots of arrows, and in the future it sort of thins out. That has always been like this because MPEG is a dynamic organization reacting to market needs, market forces, and also to technology developments. And of course, it's difficult to look into the future. So currently we are here in the middle of 2020. We are exploring extensions to VVC. Basically, we assume that machine learning can help to improve video compression. We are working on immersive video that is continuing. We assume that the second version, where the immersion for 3D objects as well as for surround views will be done somewhere in 2023. That requires video, but it also requires geometry that Marius just explained to us. In terms of audio, which we also need for complete immersion, we are looking at 6 degrees of freedom audio, where as you move through the virtual environment, the audio is rendered to you correctly, also in space and dynamically. VVC extensions regarding based on machine learning. There's also another exploration which we call video coding for machines. All these things are based on neural networks. So then the question is, how do you get the neural network to your device? Of course, the device will have some hardware implementing neural networks, but still the amount of data that you need in order to specify a neural network can be large. It can be easily several hundred megabytes. So we are also working on neural network compression, the networks specialized for multimedia. We are doing compression of static networks. We are now also looking for technology where we have neural networks for doing dynamic updates. So you have a network in your device and the service provider wants to provide an update to it. Efficient compression for that is also essential. Here we have the timeline for video coding for machine. That is an exploration. We still are not very sure that this will work out, so we are looking for technology. The goal here, or the assumption is, if the initial layers of a neural network are working on your camera device, you code the features instead of the video. Now, the features that are extracted by the initial layers of a neural network are supposed to be application agnostic. So at the receiving side, at many receiving sides, you can have your own applications working on these features and doing the computer vision tasks that you are interested in. And the assumption is that this transmission of features is more efficient than doing regular video coding. We will issue a call for proposals on the, or call for experiments in a couple of meetings. We have network-based media processing. So you want to transcode your video, transform your video, work on your video in the cloud. We specified the interfaces to do this. The second version is on its way. OMAV is sort of the systems part of MPEG-I, the interactive environment that we see the future of media going to. We will have scene descriptions extending to the new capabilities that future devices will have. We assume that it's in addition to audio, video, graphics, we will also have a haptics component there. Jens mentioned in his presentation that there is the sub-picture feature of VBC that will be supported by the video decoding interface in order to separate and merge a lot of VBC bit streams. We obviously need support for all sorts of standards that we are developing over here. And maybe at the last point, yes, MPEG started as working in compression of audio and video, but MPEG is the group which knows best within ISO about entropy coding, about quantization, about rate distortion optimization. And that is a field which you can use, or an expertise that you can use in many areas. And one area where we expanded into is genome compression, where we have the first set of standards finalized at the beginning of this year. And now we are looking further to enhance these tools for annotations and also for further compression. Genomes being one of the areas where we believe we will be expanding into the future. Big data is another area. In automotive, we all know that data transfer is a very difficult issue. With LiDAR systems, our point cloud compression will actually help a lot. And in factory automation now, also lots of data is coming up, is being stored. It becomes a problem. I assume that in the future, MPEG will also look into that area. This is a quick overview of the future. And as I said at the beginning, we expect many more arrows come here as time progresses. Thank you.